Hi there, we're taking a look at friction and Newton's laws today, specifically how friction affects the motion of an object, the ways that we can find the force of friction, and a little bit about what we call the coefficient of static and kinetic friction. The first thing about friction is how it behaves. It always opposes motion. There are a lot of forces that do this kind of stuff, but specifically when we're talking about friction right now, we're talking about the motion of one object sliding relative to another. Life would actually be really difficult without friction, in spite of our attempt to always get rid of it in a lot of our physics experiments. So it's good to ask yourself the question, what would happen without friction? Um, of course, the idea of living in a world without friction is actually kind of disturbing because there's so many things you couldn't do. Specifically, you couldn't walk or drive or ride a bike or stand or sit or hold a pencil or do much of anything because everything that you think of as slippery right now is nothing compared to a world where there is no friction at all. So if we think a little bit about how friction behaves, and we can reveal a few things by if you imagine taking an object and pulling it across the table, or at least trying to. And if you pull on it a little bit or give it a little bit of a push, but it doesn't start to move, there's clearly a force opposing your push or your pull. And that is static friction, the friction that keeps things from sliding, keeps them from moving. And if we solve Newton's second law, or first law, actually, sorry, in this case, because it's at rest, in the x direction, we would find that there is, a pulling force minus a static frictional force. And that force means that the pulling force is equal to the static frictional force. And you can pull with different amounts of force, right? You can pull with a very small amount of force or a pretty big force until it finally starts to move. And then the friction changes. You could also do this once it starts to move. Now, in that case, we no longer call it static friction, but if you could pull something at a constant velocity, you know the net force on it is zero. And so in order for the net force to be zero, the kinetic friction, we call it in this case, has to be equal to the pulling force. And this is really nice because it's a way for us to quickly figure out what those frictional forces are in situations where we have access to something like a spring scale. Static friction, there's a couple of important things about it. Because of the way it behaves, we say it keeps objects at rest. There's a little asterisk next to that because with relative velocity, we really mean at rest relative to the thing it could slide over. And it keeps growing. It goes from zero, no value when you're not applying a force, to a maximum value just before things start to slip. What we have in this video and corresponding graph is the force readout from this little force probe in newtons over time as I drag the object across the table. So if we watch the little video, right, I pull and then eventually it breaks free and I slide it across the table. We can go back to the beginning and we can actually watch the force readout as we go. I pull, it's not moving, and then suddenly it breaks free and then it moves across the table. Right? In that case, there are really three zones to worry about. There's the before it starts to move, where it's a static frictional case. There's this peak that happens when it breaks free. That's our maximum friction. And then we've got an area where it's relatively constant. And that's our kinetic or moving friction. So we can take a look at that video, an example that I just did, and kind of break it down into pieces. The first little bit, as the frictional force is building up and up and up, it's at rest. Then it lets go right after you hit the peak. That's where your Fs max exists. Then there's this relatively constant mode here where it is moving at, we would think probably at constant velocity. The fact that it's not perfectly flat leads me to believe it's accelerating a little bit there. But that constant kinetic frictional force as it gets pulled along the surface. Now, we can ask ourselves, what does friction depend on? It turns out it depends on the normal force and the materials, but let's take a look at why that works and how that plays out. We can also take a look at a few other things. We can look at the difference between an object being pulled across a table? Or what happens if I pile more mass on top of it? This is a block with 1, 2, 3, and 4 kilograms of mass placed on top. And that becomes pretty dramatic, that the more mass you pile on top, the bigger the frictional force. So it kind of makes you think, oh, is this just the mass changing? Well, we can also add in one where it's the same amount of mass as the original, as the purple one, but in this blue one, I'm actually, or I'm sorry, the pink one, I'm actually pushing down on the block instead of adding more mass. So it doesn't really matter whether we're adding mass, so to speak, because those masses don't change the mass of the block. It just changes the amount that it's being pushed down and therefore the normal force between it. So those various graphs that I just showed you, right, are all here together. We build up from the least amount of force when we just have the block, and then as we keep adding more mass sitting on top of it, which serves not to really change the mass of the block, because that can't happen, but what it does is it pushes down on the block harder, meaning the normal force increases. We can do this without placing masses on the top. These graphs came from me just pushing down with my hand while I slid it across. And so again, we can increase the normal force and therefore increase the frictional force involved. We can also take a look at what happens if instead of just being pulled across a piece of paper, we pull it across the board, right? Block on paper, block on board, different materials in contact, or maybe drag it across the table. We see that all three of these have slightly different amounts of maximum static friction force and then kinetic friction force while it's moving. It also depends on the materials, right? Here are three different pulls. There's the starting one that we've done a bunch of times, just the block on a piece of paper. Then there's the block on just the board, no paper, and then there's the block on the table. And each of these have a slightly different, Fs max, and then sort of relatively constant or constant region kinetic frictional force. So the materials involved also affect the force of friction. So the things we want to know about friction, there's kind of these four things on the list. The first three are really important. The fourth is helpful to remember. Friction always acts in the opposite direction of the motion. This is where that question, what would occur without friction, really helps, right? If something would just keep sliding forever, say to the right or to the left, then the opposite direction is the direction that friction is acting. Friction is proportional to normal force. So the bigger the normal force, the bigger the force between those surfaces. And this could be accomplished by applying a force, squeezing them together. This is how brakes on a car or your bike work between two surfaces. That affects it. Or the materials themselves. This is why, different shoes are better for gripping the ground as you're running and moving around, and why snow tires and studded tires exist for snowy, icy conditions for vehicles. The last thing is that for solid objects, and this is why it's the last one and there's no highlights, friction doesn't depend on area of contact. So it doesn't matter if you got a big block of wood or a tiny block of wood. If it's the same normal force and the same material, you should get the same amount of static and kinetic friction. For things like fluid, like once you add something like water to the picture, that's a completely different thing and gets more complicated. And area does matter. So how do we figure out values for this? Certainly we can drag things across with a force gauge, and it turns out that's really what we have to do. We can't just come up with some theory that tells us how big this frictional force will be. We have to test it. We have come up with a way of describing this we call the coefficient of friction. It gets the Greek symbol mu, a lowercase one, and that is also the symbol that is used for the metric prefix micro. Mu is sometimes how you see it written in English. It sounds like the sound a cat makes, mu. But we generally drag objects at a constant speed, and we measure that force and figure out the coefficient. And it is defined as the amount of frictional force divided by the normal force. So it's basically telling you how much of the normal force gets translated into frictional force. If you look at a bunch of different materials, this column with mu s, the static friction, you notice those are always bigger than the kinetic frictional force. Something useful and something we saw from that peak. If we were to do an example, we might say, let's drag an object across a rough, and rough is physics word problem code for there is friction. Smooth is code for no friction. It's pulled by a 75 Newton force as shown. We're given two coefficients of friction, which means we could calculate the maximum static frictional force and the kinetic frictional force that could be on this object as soon as we find the normal. Because there's nothing pushing down on it or lifting up, the normal force and the force of gravity are going to be equal in magnitude, about 150 newtons. And if it's being pulled with 75 newtons to the right, we calculate the Fs max, which ends up being 74 newtons. It's important to remember here that the static friction could be less, but we need to know what the maximum is. If it doesn't end up moving, then whatever the pulling force is, less than static friction max, is the static friction. But since the static friction max is 74 newtons and we're pulling with 75, we can say, oh, we're going to overcome that. We're going to break it away. And once that happens, it starts to slide. And we're not worried about static friction. We're worried about kinetic friction, which in this case is 44 newtons. And once we know that, we have all four of the forces that are acting on this object. And we can find our net force, pulling force minus kinetic friction, divide that by the mass to get the acceleration, and then we could solve a bunch of kinematics problems. So, what are the big takeaways from friction? Well, friction resists motion, and that's relative motion or motion relative to the ground or the reference frame. It doesn't matter, but it keeps things from sliding or resists sliding. Static friction is generally speaking greater than kinetic friction for a given pair of objects. And friction depends on two things: the materials that are touching each other and the normal force between those surfaces.